This is Design and Fabrication of an Elevator State Machine by Leonard W, Sheng Z, and Dylan Dominguez. The main goal of this project was to design and construct a model elevator that uses the cube servo as the main power source. As a team, we decided on some extra goals. We decided to implement lighting such as LEDs and 7-segment displays, a sound system with a piezoelectric buzzer, and servos that could be used to control doors. The entire project is to be controlled through LabVIEW. In this video, we'll go over our technical approach to building this elevator, including the structure of the elevator, the programming, the mechanical features, and the wiring. The first aspect of the elevator we'll look at is the construction. The elevator is made out of 3/4 inch sticks mounted on a wooden base. The cube and gearbox are secured to the top of this frame by Velcro. Our elevator car was made by a 3D printer. It's designed to slide along 4 rails on each of its 4 corners and be pulled from the center, like shown in the video. The elevator shaft is fitted with metal rods for the car to slide on. As far as the aesthetics of the elevator shaft goes, we added shiplap siding in corners, added a parapet around the roof, and a control system around the cube and gearbox. We also added doors to slide by hand and windows. The entire structure was finished off with wood stain. Looking at the mechanical system of the elevator, we originally wanted to attach a pulley directly to the cube servo. We soon figured out this would not work. The cube does not have enough torque to lift an elevator car of any reasonable weight. So what we had to do was design a 7-to-1 gearbox. We used gears from Vex Robotics and designed the rest of the gearbox around it. The gearbox connects to the cube servo using a magnetic boot that is designed in the same way as the attachments that Clonzer sends with the servo. This magnetic boot connects to the gearbox through a metal rod and connects to the 12-tooth gear. This 12-tooth gear drives an 84-tooth gear, which is connected through another metal rod to the pulley. This system increased the weight that we can lift from about 1/4 pound to nearly 2.5 pounds. The next system we'll take a look at is the circuitry besides the cube servo. To implement all the lighting and sounds and other servos we wanted to add, we used an Arduino Mega 2560, which is controlled through LabVIEW with an extension called Links. This Arduino can't draw enough power out of the USB port by itself to drive all of the lights we wanted. So what we had to do is design a PMOS driver circuit for each set of LEDs that connects to a 5-volt external power source and is just signaled by the Arduino to turn the lights on and off. The piezoelectric buzzer doesn't really require much current, so we directly connected it to the Arduino. The small hobby servos have 3 wires. 2 are a 5-volt and ground, and they connect directly to the power source. The other is a signal wire. It connects directly to the Arduino. The Arduino sends a signal with a certain pulse width down this signal wire, which controls the servo. This PMOS driver circuit and the Arduino are connected to the electronics on the front panel through DuPont cabling. Now let's take a look at the programming of the elevator. The language we used, per the project requirements, was LabVIEW. The cube servo is controlled through the Clonzer RCP toolkit. The Arduino is controlled through the Links extension. At the highest level, this program is written as a state machine in LabVIEW. This is a while loop with shift registers and a case statement inside of it. This is programmed so that every iteration of the while loop, the case statement goes to a different state. As you can see from the state diagram, Our elevator starts out in an initialization state. It then transitions to the stopped floor 1 state. There's a stop state for each floor of the elevator. These states all transition into a link state, but this is just a result of the control and simulation loop programming that I'll get into a bit later. Really, these stop states transition into each movement state. Each stop state can transition into the corresponding movement state, and then it will transition into a different stop state once it's completed the movement. There's also a doors state, which accesses links and opens and closes the doors. In all of these states, besides links and doors and initialization, there's a control and simulation loop, which is where the elements from the Quanzer RCP toolkit must be. These functions include reading the encoder value from the servo and writing a voltage to the servo. The way these control and simulation loops works is that first, the encoder value is read from the cube servo. This value can be positive or negative, so we put it through a function to make it completely positively valued. We then set an angle for each floor. The measured angle is then subtracted from this desired angle to get the difference. This difference is put through a function that sets a voltage according to the difference. For example, if the elevator is at floor 1 and the desired floor is floor 3, there's a 10,000 degree difference. This function maps 10,000 degrees to a positive voltage that will lift the elevator car. We'll call this value the base voltage. The base voltage by itself isn't enough to lift the elevator car if it's loaded. To compensate for this, we must add in some sort of correction factor. To do this, we took the derivative of the encoder angle. This derivative represents the velocity of the encoder. This velocity is compared against a desired velocity, and then this difference is integrated and multiplied by a gain. This is the correction factor. The final voltage read into the servo consists of the base voltage times 1 plus the correction factor. So, in the end, the result is a scaled version of the base voltage. Many of these control and simulation loops have tweaks to make the control system more stable. You can see more about these tweaks if you look at the comments in the programming. Outside of the control and simulation loops in each state is the logic that controls the state transitions. This is all controlled through Boolean buttons on the front panel. One caveat to this is that the control and simulation loops do not allow any other code to execute while they're running. So what we did is we have buttons that are only visible during these loops, and they look exactly the same as the default buttons. We use these buttons to control the queuing and interruption features of the elevator. You can see the code for more information on how this works. The last aspect of this program is the Arduino control. The Arduino is controlled through links through its own separate state. This state uses the value of the last state and the next state after it to determine what to do with the Arduino. It's very simple how the Arduino is controlled. Digital Boolean values are written to the output pins through a links control. It's that simple. This concludes our technical video on our elevator. For more information on mechanical and structural aspects, see the final report. For more information on the programming and LabVIEW aspects, the comments in the code are the most thorough place to see.